(1956), Minamata Bay, Japan. Near a seashore, children stopped their play to watch a strange sight. A cat, contorted with grotesque jerking and leaping movements, ran across the field and in a sudden violent lurch threw himself into the ocean to be swallowed up and drowned. 2004, Kunming, China. Students in this inland city are on the average healthier and more intelligent than their parents and grandparents. One of the reasons for this better health and higher intelligence is the more adequate amounts of the elements iodine and iron that they now get in their diet, chemicals that were lacking in their parents' and their grandparents' diet. 2024, Black Earth, Wisconsin. The local farmers' cooperative had a closeout sale on all remaining nitrogen fertilizer, final 3 tons going for 10 cents on the dollar. The co-op's new hybrid corn seed, on the other hand, was in short supply this spring because of the high demand. Farmers throughout the Corn Belt are finding that the nitrogen-fixing ability of the new corn hybrid has almost eliminated the need for artificial fertilizer on their cornfields. This is the story of chemicals in the living world, in our biosphere. The story of chemicals, good and bad. First, the bad. It was in 1956 that the citizens of Minamata, Japan, first began noticing the strange behavior and the diminishing numbers of cats in town. And people began coming down with a strange new disease that seemed to affect the nervous system, leading to convulsions and sometimes to death. Over the next 20 years, a grim story began to unfold as more people were affected in and around Minamata, including children born defective from mothers whose diet included substantial quantities of locally caught fish. And eventually the truth came out. A local chemical factory had for years been discharging into Minamata Bay waste chemicals that included small quantities of mercury. Over the years, the mercury had been taken up in the food chain, concentrated, and changed into a deadly form of methyl mercury that lodged in the flesh of fish. When the fish was eaten by cats or people, it was the methyl mercury that acted so destructively on the nervous system. Well, Minamata was one of the worst examples, but this story has been repeated in other parts of the world with other chemical wastes, so that it is no wonder some people today are extremely wary of any chemical. And yet we know that chemicals can be useful as well as harmful. Chemicals like soap and gasoline, paint and film, aspirin and penicillin. And then when you get down to it, all natural products like paper, wood, cotton, wool, leather, and honey are just as much chemicals as plastic and ink, as fertilizer and drugs. That is, all of these are made of carbon and hydrogen, of oxygen and nitrogen and iron. And when you really get down to it, oranges and apples, rabbits and horses, you and I are made of chemicals. We are chemicals. And just as more knowledge of chemicals in the biosphere can lead to ways of preventing any more Minamatas, so too it can lead to a multiplication of Kunmings and of Black Earths. We didn't explain the good chemicals examples yet. The good news takes longer to make interesting. The details of both the Kunming and the Black Earth stories, and many thousands of others, get ahead of our story. The role of chemicals as they cycle in the biosphere. But to understand the Black Earth story, we first need to, well, start with air. We can survive a few weeks without food, a few days without water, but only a few minutes without that delightful mixture of chemicals we call air. Specifically, air is a mixture of four main chemicals: oxygen, 21%, nitrogen, 79%, carbon dioxide and water vapor, less than 1%. Air also has very small quantities of other chemicals, some put there through natural processes and some through human-initiated processes. Each of the four major gases in the air is absolutely essential to the life of the biosphere, and each one is in continual movement into and out of all living creatures. Oxygen, for instance. As you listen and watch these words and pictures, oxygen molecules from the air are coming into your lungs, going into your blood, are carried by the blood to your heart or brain or big toe, there to be cleverly combined right now with food to give you energy. Now, those same oxygen atoms that you just used were only very recently combined with hydrogen atoms in a water molecule in the soil. The water was taken up into the leaf, and in the process known as photosynthesis, the oxygen part of the water suddenly found it dumped out into the air. In this case, the oxygen was a waste product so far as the leaf's photosynthesis was concerned. Note that in this diagram of the oxygen-carbon dioxide cycle, the oxygen atoms keep changing partners as they move into and out of plants and animals, into and out of water, the soil, and the air. If you were to follow just one single oxygen atom, let's say, it might start coming out of the tree leaf and move into the cow's lungs to be used by the cow's cells in respiration. Then it's breathed out, now hooking up with carbon in carbon dioxide, CO2, where it goes into the air, perhaps back to the leaf, and is used in photosynthesis. When the sun is shining, plants are continually using carbon dioxide and water to produce sugar and oxygen, while at the same time plants and animals are continually using sugar and oxygen to produce carbon dioxide and water. So you see, photosynthesis and respiration are two co-equal complementary processes. Besides the living respiration, other natural processes on the globe also fix oxygen into carbon dioxide and water, especially fires, whether in furnaces, in an automobile engine, or in a campfire. These all make oxygen from the air join with carbon and hydrogen and nitrogen to produce carbon dioxide, water, and nitrogen oxides. So too, the natural corrosion of metals takes oxygen out of the air, forcing it to combine with metal atoms to form rust, which is iron oxide, aluminum oxide, copper oxide, and so forth. And finally, in the special case of decay, certain bacteria need oxygen to live and carry out their essential function in breaking down the complex chemicals in dead plants and animal remains. The oxygen-carbon dioxide cycle has been going on with little change for many millions of years on Earth. In just the last 100 years, this cycle may be changing, slightly but significantly. The rapidly increasing number of fires from furnaces, power plants, and especially from automobiles, trucks, and airplanes have been putting carbon dioxide into the atmosphere in greater quantities than the plants, corrosion, bacteria, and ocean water take it out. Many experts think that this may lead to a gradual warming of the atmosphere. Well, this global warming could have dramatic effects on human activities everywhere on Earth. Let's turn now to another important chemical cycle, the nitrogen cycle. About 79% of the air is pure nitrogen gas, N2, 2 atoms to the molecule. Now this nitrogen does not stay pure N2 for long, but it also participates in the dance of life. Nitrogen gas, N2, is, however, relatively inert chemically. That is, it does not easily combine with other atoms to make compounds. We say it is difficult to fix. Now, all living creatures are constructed. That is, they are literally built out of nitrogen-rich chemicals called proteins. And they are operated with nitrogen-rich chemicals called enzymes. Both proteins and enzymes have nitrogen atoms as key parts of their structure. So a general problem for life is, how do you get the nitrogen atoms from the air fixed into the nitrogen proteins and enzymes of life? A first guess might be, why not just breathe it in like oxygen and let it do its trick in the blood and cells? Unfortunately, it won't work. The nitrogen you breathe in just gets breathed right back out, unchanged, unfixed. So how do you get it into your cells then?
Well, the answer is you can't, but certain special kinds of bacteria can and do. Fortunately, there exist in the biosphere large populations of nitrogen-fixing bacteria that almost alone among living things are able to take nitrogen in its pure air form and through their living metabolism make that nitrogen combine with hydrogen, to fix it, in other words, into ammonia, a molecule of 3 atoms of hydrogen to 1 atom of nitrogen, NH3. Other microorganisms are able then to add oxygen to the ammonia and change the ammonia into nitrites and nitrates. And these nitrogen-rich compounds can then be used by plants to make the very large life-forming molecules called proteins and enzymes. Now these plant proteins and enzymes in turn can be eaten by animals like us to make animal or human proteins and enzymes.
However, unfortunately, so far these bacteria will only thrive in certain special niches on Earth. The roots of leguminous plants like beans, peas, clover, alfalfa make good homes for the nitrogen fixers. Also, some varieties will live in blue-green algae and even in some soil. Now, the big news recently is that they have been coaxed into living on special hybrid corn roots, too. At last, the Black Earth story. This latest breakthrough has only very recently happened at the University of Wisconsin and a number of other agricultural research laboratories around the world. And not only corn, but also wheat, rice, and other important grain crops are being studied and experimented with in the hopes of coming up with varieties that will harbor nitrogen-fixing bacteria on their roots.
This may someday lessen or even eliminate the need for nitrogen-rich chemical fertilizers, which in turn could lead to less air and water pollution, more efficient energy use, and increased agricultural production. A caution, however, the Black Earth story takes place in 2024. The breakthrough looks promising today, but a great deal of research and development needs to be done before such nitrogen-fixing corn hybrids will actually be available for farm production.
Because this nitrogen cycle is so important and often misunderstood, let's summarize it once more with the help of this diagram. Gaseous nitrogen can get fixed into the soil by nitrogen-fixing bacteria or by natural decay processes. In the form then of ammonium, nitrates, or nitrite ions, it is taken up by green plants, then eaten by animals, which build these chemicals into proteins and enzymes into their own flesh and blood. The animals and plants in their turn die and decay and have their proteins and enzymes broken back down into ammonium, nitrates, nitrite ions, which is why so-called organic fertilizer, cow manure, compost, organic wastes, are useful as fertilizers. Of course, we should also make clear that ammonium or nitrate ions can also get into the soil by way of commercial chemical fertilizers. These are made in a chemical factory, which is also able to fix nitrogen from the air into ammonia by way of an ingenious human-invented process. It's called the Haber process. Finally, there are also denitrifying bacteria, which complete the cycle by breaking down the ammonium and nitrate and nitrite into gaseous oxygen, nitrogen, and water. And so our nitrogen cycle is complete.
Now, nitrates are not the only nutrient that plants need. Chlorophyll, for instance, the key molecule in photosynthesis, needs small amounts of magnesium. Other plant molecules need phosphorus, calcium, sulfur, iron, copper, potassium, sodium, iodine, and about 15 more common elements in small traces. All of these must also be absorbed into plant roots from the soil, and all of these have their own simple or complex cycles in the biosphere. Sometimes, for instance, the soil in a given area may be deficient in certain elements. Iodine, for instance, is common in fish and seafood and in soils near the ocean. It is often, however, in short supply in inland soils. So vegetables and animal products grown in many of these inland areas do not get enough iodine. Well, when humans have to rely solely on these local food supplies, humans do not get enough iodine, and this deficiency can result in diseases of the thyroid gland, and more important, in a lowering of intellectual capacity by as much as 10 to 15 percentage points. Similarly, about 40% of the developing world's people suffer from a deficiency of another trace element, iron. This lack of iron in the diet can result in similar drops in children's IQs. Right now, the United Nations Children Fund is sponsoring projects to artificially fortify foods with iodine, iron, vitamin A, and other trace elements and compounds needed by the human body, but often absent or severely restricted in the diets of poor people around the world. Now, deficiencies in the soil are not the only problem with trace elements. Plant cells can be fooled into accepting dangerous substitutes for the real thing.
Instead of selecting and concentrating the needed calcium, for instance, they will accept a very similar element, strontium-90, which is highly radioactive and capable of doing damage to any living cell. As the plant cells concentrate the strontium-90, they in turn are eaten by animals who further concentrate it, in their bones in this case. And still more concentration happens, and so it happened in Minamata Bay with mercury. Up the food chain through algae to small fish to large fish to cats to humans.
Well, today in the 21st century, ecologists warn that mercury is still and again a dangerous chemical when it cycles through the ecosystem and becomes selectively concentrated, especially in fish. Now, coal contains mercury. Coal-fired power plants around the world are prominent mercury polluters. New federal regulations in the United States require new kinds of filtering equipment on power plants to cut back on the emitted mercury. This country, Canada, Japan, and Western Europe have made rapid strides in controlling this chemical, but there is still more work to be done. Unfortunately, developing countries like China and India are building new coal power plants that often do not include this filtering equipment. Mercury is just one example. Many other chemicals in small quantities cycle through the biosphere. Most of them are helpful, indeed essential to life on Earth. Some of them can be harmful. Pesticides like DDT, for instance, cycle through the soil, mosquitoes, birds, into birds' eggs, and lead to near extinction of some bird species. PCBs, polychlorinated bipheноls, created in factories, cycle into your salmon, or your milk, or your breakfast cereal. Sulfur and nitrogen oxides emitted from coal-fired power plants dissolve in rainwater and lead to an acid rain that may harm some forested areas. Then lead, asbestos, herbicide residues, and radioactive chemicals from natural rocks, from nuclear plants, from coal-fired power plants, and from outer space all continually cycle through the biosphere. In some cases, the quantities of these dangerous chemicals are so small that it has been difficult to prove much harmful effect on living things. In other cases, higher concentrations of chemicals like lead, mercury, and asbestos have caused serious health problems. Research and control efforts are continuing, and there are problems and honest disputes within the scientific community as well as the political community about the possible effects of these chemicals. Farmed salmon, for instance, because of the way they are fed in confined pens, have PCB levels higher than wild salmon. On the other hand, these levels are still far below the limits set by the federal government as being safe to eat. In addition, most of the PCB contaminants are in the skin of the salmon and the fat just beneath the skin, parts that most people do not eat. Surprisingly enough, in some cases of both chemical and radiation exposure, new research has shown that very small amounts may not be harmful at all. In fact, they may actually be beneficial to living things.
In most of these cases, the offending chemical is carried in the last of our key naturally cycling chemicals, water. And this is the final component of our air, too. Water moves into and out of all living systems, so much so that the ancient philosophers thought all living things were made of water. We are made of some 70% water, and inside our living bodies, water is not only used directly in being a part of chemical reactions, but it is also an essential carrier of all the other chemicals. Here you can see how the water cycle works on this spaceship. Notice that if you were to follow a single molecule of water, it would make a fascinating world journey. Up out of the ocean into a cloud, floating across the continent to fall on a mountain peak as snow, melting down in the rushing stream, or perhaps sinking into the ground to become part of the water table, surfacing in springs, ponds, marshes, but slowly finding its way back to the ocean. The most subtle and interesting part of water's cyclic journey is its path into and out of living systems. Here it is inextricably intertwined with the oxygen-carbon dioxide cycle. From the tree's roots into the leaf, built into sugar, eaten by an animal, burned in the mitochondria of the animal, released again as waste product water, into the blood, out the lungs, or excreted by the kidneys, back to the air, back to the earth, back to the ocean. And so the eternal cycle of water goes on and on and on.
Chemical cycles in the biosphere. An old story, but one always surprising us with new chapters. Oxygen, hydrogen, nitrogen, carbon, phosphorus, iron. All these and 15 to 20 more of the most common elements have been built for millions of years into the delightful architectural combinations of chlorophyll, glucose, adenosine triphosphate, cellulose, lysine, and the millions of other enzymes, salts, acids, and diverse chemicals that we call a leaf. And the same chemical elements have been built for millions of years into other architectural combinations of hemoglobin, glycogen, lysine, thymine, guanine, adenosine triphosphate, sugar, salt, and the millions of other enzymes, proteins, acid, and nutrients that we call a hand or a brain. So, operating rules for small spaceships. 1, don't be unduly afraid of chemicals. You are made of chemicals. Learn to tell the good from the bad, and learn to enhance the good and diminish the bad. Number 2, on a spaceship like Earth, you cannot throw anything away. There is no away. At best, you can shove it into an unused closet where it could be dangerous or useful in years to come. Learn and plan for today and tomorrow.
And rule number 3, take time out occasionally to feel the air, the earth, the water, to feel the chemicals in your own chemical body.